Okay, we are going to take a look at just a few other factors that will affect reaction rate. The next one being pressure. So we'll look at low pressure versus high pressure. And the rule of thumb is that if you have a container that has a greater pressure, that will decrease the volume. So here you can see there's a top on this container. And when we push that top down, we're increasing the pressure, which decreases the space available for the molecules to move. If there's less space, that leads to more collisions. It's like having your entire class be around the entire classroom. Not a whole lot of collisions would occur. But if I made your entire class walk within the confines of just a very small space in the classroom, a lot of collisions would occur. So the greater the pressure, the more collisions there will be, and therefore the faster the reaction rate. So greater pressure leads to faster reaction rate. All right, if we take a look at temperature, low temperature versus high temperature. High temperatures mean that particles have more. So, temperature is average kinetic energy. So, if we increase the temperature, not only are those particles going to collide more frequently, but they're also going to collide with more force, which means more of those collisions will be effective because they will have enough kinetic energy to overcome the activation energy. And what I have here is a picture of a demo that I usually do, and it's just involving glow sticks and water. So I'm sure you're all familiar with glow sticks, and all this glow stick in cold water and then a glow stick in warm water. And a glow stick, you typically have to crack it in order for it to start to glow. That's a chemical reaction that's occurring. And when that reaction starts to occur, we can speed it up. We can make it happen faster by putting it in warm water because the warm water increases the kinetic energy of the molecules inside the glow stick, and therefore the reaction will happen faster. I use store glow sticks in the refrigerator or in the freezer when you want to save them because putting them in the freezer slows down those particles and they're not colliding as often. And therefore, the chemical reaction can happen for a longer period of time. It's really the whole idea behind the refrigerator. Food going bad, decomposing, is a chemical reaction. So when you keep food in the refrigerator, you're preventing that chemical reaction from happening at a fast rate. It will still occur, your food will still spoil, but by keeping that reaction down. So higher temperature, faster reaction rate. Okay, and we're also going to take a look at a chemical reaction that you can actually see between vinegar and baking soda. We are going to demonstrate how the temperature of a substance affects the reaction rate. So what we have here is and then a cup full of warm vinegar. So this I just put in the microwave for about 30 seconds, and the cold vinegar has been in the refrigerator for the last few minutes. And then I also have equal amounts of baking soda that will go into each. When I pour the baking soda into the vinegar, a reaction will occur, and we'll see if there's any difference based on the temperature. So you could clearly see that the warm vinegar, that reaction happened much faster. All right, and lastly, the factor that we have yet to talk about that will affect the reaction rate is the presence of a catalyst. So you saw this in the very first video that you watched about finding a date to the dance. And a catalyst, and we have a bit of a typo here, I apologize. A catalyst That's what that should say. It lowers the activation energy, meaning that it requires less energy for the reaction to occur. And if it requires less energy for the reaction to occur, the reaction will happen faster. So a catalyst speeds up the rate of a chemical reaction. And what we have here is a potential energy diagram. We'll take a closer look at this in future lessons, but a potential energy diagram traces the potential energy of the reactants into the products. So over here we have the potential energy of our reactants, and then this referencing before, kind of like a roller coaster, that's the activation energy. So in order for this reaction to happen, in order for the products to form, the molecules have to have enough energy to get up and over this hill. If they can't, the reaction doesn't happen. All a catalyst does is it brings that hill down. It doesn't change the amount of heat that the reactants have. It doesn't change the amount of heat that the products have. It just changes how it gets there. And so this is going to lower the activation energy, and in doing so, the reaction will happen faster. And this is also one of my favorite demos of the year. It's called elephant toothpaste because it looks like toothpaste that an elephant would use because it's so large. And the video that I have linked here does talk about the catalyst, and it talks about hydrogen peroxide. So the decomposition of hydrogen normally over time. So it's in a brown bottle because it's sensitive to light, and it also has an expiration date. That expiration date is there for a reason. Hydrogen peroxide will decompose into water and oxygen over time, which makes it not very useful for antiseptic purposes. However, you can speed up that decomposition by using a catalyst. And a typical catalyst for this reaction is something like sodium iodide. And in the video, you're going to see not only do they put the catalyst into the peroxide, they use a much more concentrated version than you can buy at the store. And they also put dish soap in there. And the dish soap is to capture the oxygen and to truly give you a visual of how much oxygen is being produced in the decomposition and how fast it happens with a catalyst. So enjoy.
Are you ready to imagine it? This one is so huge, Carl had to blow the lid off the place. We're out in front of the IS, the Imagination Station, not to be confused with the ISS, but I think they might see this from space.
We have some
Hey,
technical
Carl, what are you
difficulties.
cooking up?
Well, today we're going to talk about hydrogen peroxide. It's the stuff you have in your medicine cabinet, right? You pour it in a cut and it bubbles. And the reason it bubbles is because the hydrogen peroxide, H2O2, comes in contact with catalase in your skin, which breaks down the hydrogen peroxide, turns it into basically water and oxygen gas. Okay?
I can say okay, but you lost me.
Yeah, well, let me show you what happens here. So this is just a bigger scale version. This here is 3% hydrogen peroxide. What we're using over here is 35.
Oh.
So it's much more concentrated. I have a catalyst in here, sodium iodide, and we're going to pour that into the hydrogen peroxide just to see what happens. Okay?
Sure.
Because it should catalyze it and cause it to break down. So I'll pour a little
Let's
in.
just see.
Step back.
Whoa.
Yeah.
Catalyzed all over.
And look at that steam, right? This is an exothermic reaction. All right, so we're generating heat. We generated lots of oxygen gas there. But for me, it was a little disappointing because I really want to capture those bubbles in some soap.
Of course you do.
And then we can make a foam. Okay? So same deal here. We've got some hydrogen peroxide, 35%, some Dawn dish soap. I'll just add the dish soap into there. And I'm going to give you the honor this time, Tony.
Excellent.
Of adding the catalyst. Now, wait just 1 second. I'm going to take the cap off. I'm going to give this to you. Catalyst, go ahead and pour it in. Let's see what happens. Just dump the whole thing in. We release the oxygen inside, and you can see we generate lots of foam. It's a giant blob of oxygen-filled, soapy foam,
Yeah.
which is really cool.
It is. It's like Ghostbusters 2.
Exactly. But now, I want to take this one step further. I want to change another variable here. Instead of doing this in a big graduated cylinder, I have set up down here 6 flasks, which taper near the top. And what I'm hoping for here is that And it's going to go for a while. What I'm hoping here is that as we generate this gas, it is going to generate some pressure. And inside each of these flasks, we should get a jet of foam shooting out. Okay? But one more thing. Everybody knows Roy G. Biv, right?
Right. We're going to go the rainbow color.
We're going to go the rainbow colors. So we're going to add some rainbow colors here. Now, I'm a little concerned about that foam. Might have a catalyst here where this is dangerous.
Oh, boy.
Let's see if anything, nothing.
Gingerly pour.
Gingerly pour. Okay, so I'm going to add the food coloring into this one. We got a red. I'm going to let you add the next one.
Thanks.
I'm going to take the next. And Sarah Gulch down here is going to help us with the other. So
Hi, Sarah.
we're just adding food coloring. We've already got the soap in there. And this is a generous pour of food coloring, probably more than you'd ever have at home. Okay, I think we're all set up. Now, you saw what happened with that ball of foam. You're probably not going to want to put this microphone, which is probably pretty expensive.
I'm going to set it down.
Be careful with that.
Sure.
We each have 2 catalysts. We're going to do a little countdown. You're going to take 2 catalysts, and you're going to pour quickly into there, okay?
Okay. Before we do that, I just want to go over the basics. If you're heading on down to the Imagination Station, here are the hours on your screen. They are downtown, of course, at One Discovery Way. And if you live in Lucas County, kids get in free with a paid adult admission. That's kids 12 and under. Now, we're about to set down the microphone so we can conduct this experiment. We're going to talk really loudly as we do so.
Let me hand these to you.
Okay,
I'll take
thanks.
the tops off
Do the
for you.
hand off.
Do those
All
hands.
right.
Just hang on one second. Let's
Yeah.
make sure I have mine ready, because once we do this, there's no stopping. This is
This
kind
is
of a one and done kind of
one and done. This is the only
thing.
shot.
I've got 2. Sarah's got 2. You've got 2. You know
All
what?
right.
These are a little bit. They lost.
Top me off
I'm
there.
gonna top you off with extra catalyst. Okay, we'll get rid of that one. All right.
Okay, setting down the mic now.
All right.
Okay.
So here we go. Elephant's toothpaste. 3, 2, 1, pour. Step back. Hey! Yeah. All right. So, again, 35% hydrogen peroxide. We're using sodium iodide to catalyze the reaction. We added some food coloring. All those bubbles are filled with oxygen gas. It's just a classic.
It's a brightly
It's a
colored mess.
classic.
Take a look at the ground too here. Hopefully this will be cleaned up by the time
Oh,
you head on down to the
I'm-
Imagination Station.
I'm sure a little rain will come by and clean all this stuff up. We'll come out with some water. But look, it is still going, like you
Oh,
said.
it's so
And so we are
fascinating.
building up that beautiful